4.2 Greatest Common Factor. The objective of this lesson is to find the greatest common factor of two or more whole numbers. Vocabulary. The common factor is a whole number that is a factor of two or more non-zero whole numbers. So let's take 6 and 12 for example. So all the factors of 6 are 1 and 6, and then 2 and 3. And for 12, we have 1, 12, 2, 6, 3, 4. Okay? So all the common factors of 6 and 12 are 1, 2, 3, and 6. And since 6 is the biggest one, we call that the greatest common factor. Okay? And relatively prime just means when you have two numbers such as 3 and 8 who only share a common factor of 1, which is also the GCF. Okay? So we will remember we have on the test you will have to write RP and GCF of 1. Okay? Guided practice, part A. To find the greatest common factor, use the cake method and divisibility rules. Okay? So 12 and 30. The lowest common prime factor of 12 and 30 is 2. So we will begin with 2. 2 times 6 is 12. 2 times 15 is 30. And the next one we'll have 3, 2, and 5. So we can't go anymore. So the greatest common factor will be 2 times 3, which is 6. And for 21 and 42, we would use 3 first because that's the lowest common prime factor between 21 and 42. And moving down, we have 7, okay, and 14. Okay, and then our greatest common factor will be 21. The next one, 16, 32, and 40. Let's start with 2. Okay, and then we have 16, and then 20. Keep using 2, 8, 10, 2, 2, 4, 5, and then we stop here, and then our greatest common factor is 2 times 2 times 2, which is 8. Okay, and then the next one we have 27, 45, and 90. We begin with 3, 9, 1, 15, and then 30. 3, 3, 5, 10. And then we have a greatest common factor of 3 times 3, which is 9. Okay? Now, moving down, we're going to continue to find the GCF of the numbers, but these are a little more difficult. And then we have to tell whether these numbers are relatively prime. Okay, so I'm going to use the cake method together or separately. So what do I mean by together or separately? So let's start with 18 and 33. They share a common factor of 3. So that's the only one. GCF is 3. And 39 and 50. The sum of the digits of 39 is 12, 5. Then these two numbers don't share any factors other than 1, so we would say they're relatively prime, and then GCF of 1. Okay, here we have 11, 10, 7, and that's it. So our greatest common factor is 11. Okay, and look at 115 and 207. It doesn't seem like I could determine a small common factor between these two numbers other than 1. So I'm going to do this separately. Okay, hopefully I'll find something. So 5, 2, 23. Okay, I have to stop here. Start with 3, 6, 9, 3, 2, 3. Oh, I found the 23. So that's the GCF. Okay, GCF of 23. Okay, and then let's move down. Okay, now we need to find the GCF of the monomials. Okay, between 18 and 28, we need to find the GCF. 2, 9, 1, 4, and that's it. So our GCF is 2. Let's write that down here and put a dot. And we have x and x squared. We got to take the smaller one. And then we have y squared. That's our GCF. And to show you the full cake method, I'll put it right here. We should get the same answer. 2, 9x y squared, 14x squared y squared. Let's take out x, 9 y squared, 14x y squared. And let's take out y squared, 9. Okay, and 14x. So 2 times x times y squared will be the same as your answer here. Okay, but you have to show all this work. It's crazy. I wouldn't recommend this way. Okay, so practice. The GCF between 7 and 28, it's obviously 7. And you have x and x, take that one time. You have y cubed and y squared, you take the smaller power. Okay. Okay, this one, it can be a little tricky. And we have r, but the middle monomial does not have an r. And we have an r squared. But because of the middle monomial does not have an r, we can take r out. Okay, we're going to cross out r. Okay, and now we have s cubed. Excuse me. We have s cubed, and s, and we want the smaller power. So s, and then we have t squared. T, but the first monomial does not have a t, so we need to take the t out. So that's where we're left with s. And if you're still unsure of what I just did, take a look at this. R, S, S. Let's factor every single monomial. Okay, and look, we have to look for that common factor in which all 3 monomials share. So it seems like S, we see one here. R, we don't see any. Cancel, cancel. And there are no more S's. And T, there's no T in the first monomial, so we cancel. There's only S. So that's the greatest common factor. Okay? So, in conclusion, if a monomial does not share the same factor, then we need to kick it out, okay? Can't include it. So all 3 monomials have to share at least one common factor. Okay? So what do I mean by that? if I gave you the problem 7xy cubed 28xy squared, and I'm going to add a z here. Okay, let's say. Then our greatest common factor will still be 7x. Okay, we keep the x one time, and we take the smaller power y squared. We do not keep the z because 7xy cubed does not have at least one z factor. Okay? Okay, let's move on. Music camp. A summer camp has 88 participants. The camp has 32 vocalists, 16 drummers, 24 guitarists, and 16 bassists. What is the greatest number of identical bands that can be formed using all the participants? And how many vocalists will be in each band? So we have 32 vocalists in all, and we need to find out how many are there in one band. Okay, so we need to find the greatest common factor between 32, 16, 24, and 16. 32, 16, 24, and 16. Okay, let me make this clearer. 2, 16, 8, 12, 8, 2, 8, 4, 6, 4, 2, 4, 2, 3, 2, and we stop here. So the greatest common factor would be 2 times 2 times 2, which is 8. So 8 would be the greatest number of identical bands. Okay? And the 4 here tells me that I will have 4 vocalists in each band. Okay? Now, let's move down. Flower bouquets. The Science Club is selling flowers for a fundraiser. The club wants to make bouquets from 4 types of flowers. The bar graph shows how many flowers of each type the club has. What is the greatest? Okay, this key word right here. What is the greatest number of identical bouquets that can be made? And what will each bouquet contain? Okay, let's look at the bar graph here. Okay, we have 14 as the interval. Okay, so here 56 plus 7 would give me 63. And here we have 56. Here we have 42. And here we have 21. And then we need to find the GCF between all 4 numbers. 63, 56, 42, 21. And I see that they share a lowest common prime factor of 7. And we move down to... Okay, and then we stop here, because we can't find any more common factors between all 4 numbers other than 1. 7 is the greatest number of identical bouquets you can make. Okay, and then in each bouquet you'll have 9 daisies, 8 lilies, 6 irises, and 3 freesias. Okay, and this is the other part of your answer. Alright, now let's look at the last word problem. Community garden. You want to cover the walkway of a community garden with square, okay, clay tiles. The space you want to cover is a rectangle, so I'm going to draw a picture. 42 inches wide, okay, and 72 inches long. Assuming you want to cover the space exactly without cutting any tiles, so if we fill in all these tiles, these would all have to be squares, okay, and we're not going to cut any of them. What is the greatest side length you can use for the tiles? So what we're looking for here is the greatest side length of each tile. Okay? So we need to take the number 42 and 72. 42 and 72, and we need to find the greatest common factor. 2, 2, 1, and then we have 36. And we're moving down. Okay. 3 times, 12. And then we stop here. So we take 2 and 3, we multiply them together to get a GCF of 6. And it will be inches. 6 inches per tile. Okay, well 6 by 6, okay? So then the problem does not ask for how many tiles per side, but we know that the width is 42, so we need 7 of these here. 1, 2, 3, 4, 5, 6, 7. And we'll need 12 here. 5, 6, 7, 8, 9, 10, 11, 12. Okay? This number tells me I need 7 square tiles for my width, and then 12 square tiles for my length, and then they are 6 inches. Okay, per tile. And then that's it.